Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you today, as it is every day here in my virtual classroom. Step on inside as we cap off Chapter 9 base material in the Big Ideas Math Integrated Math 2 textbook with the Chapter 9 test and cumulative assessment. I will break this thing up in the description section down below with two separate PDFs, one for the Chapter 9 test, one for the Chapter 9 cumulative assessment, or the cumulative assessment, if you will, because it's all chapters 1 through 9, and of course with the timestamps if you're trying to find something very specific. I more want to do these problems than teach them. Yes, I'll teach as I do, but we should have heard them before. I might say what section something's from and how we can recall it, but kind of want to just do the problems more so. The only other video that might pop up here from Chapter 9 is an Are You Ready video. I've been doing them, I believe, since Chapter 6 because my colleague's been making packets of reviews, and it's for my students as well as just anyone else who wants to listen, but it's not from the textbook itself. Without further ado, guys, let's go ahead and get started and see what we got. We're going to begin with numbers 1 through 18 on the Chapter 9 test portion of this. Numbers 1, 2, and 3 ask find the value of each variable, round your answers to the nearest tenth. This is not out of section 9.1. This is actually out of probably section 9.5 or 9.4. This is trig. And I like that these things are used in such a way that they are not in a vacuum, if you will, because are we using sine or cosine, or are we using tangent? Tangent was just 9.4, right? So with this first problem here, and I think I want to copy paste these. If there's a little bit of slowdown, it's going to be now. I want to copy paste these guys and figure out what we're looking at. We got the 25-degree angle and this 18. With that in mind, t is opposite as 18's hypotenuse. I can use sine as a setup here. Sine of 25 degrees equals t over 18. Multiply both sides by 18. You get t is 18 times sine of 25 degrees. Use your calculator for this part. Make sure that you are in degrees on your calculator. And I'm getting 18 times the sine of 25 degrees to be 7.6. Yeah, around 7.6. So there's t. S, on the other hand, is adjacent to the 25-degree angle, and then we have the hypotenuse of 18. Let's use those ones. That's cosine. Adjacent S over hypotenuse 18. So S equals 18 times the cosine of 25 degrees in this case. And 18 times the cosine of 25 is longer. It is 16.3, around 16.3 units. And that's number 1. Number 2. On number 2, this time, sorry, I have to still get things set up. Copy, paste. Let's get that image. There we go. Okay. If I want to find x, I want to use the 6 opposite the 22, and x is the hypotenuse. I want to use sine again for a scenario like that. Let's highlight that in blue like I did last time. So sine of 22 degrees equals 6 over x. Now x is in the denominator. This is that switch place thing. Multiply both sides by x, divide both sides by 22. It's 6 over sine of 22, not 6 times the sine of 22. And you should know it should be longer than, it should be the longest length here. So 6 divided by sine of 22, I'm getting 16.01, so 16.0 as a rounded value for x. Y is a different scenario this time. Assuming I'm not going to use the x, I will use the opposite 6, but y is adjacent to the 22 here. So I want to use tangent in this scenario here. Tangent of 22 degrees is 6 over y, and the same thing as y switches places with tangent, 6 over tangent of 22 is what we're going to be dealing with here. So I will use the calculator once again and work that guy out, 6 over tangent of 22, and I'm getting 14.85, so around 14.9 units on that guy. And there's y. And 16 is the largest value. It should be. It's the hypotenuse. That's number 2. Number 3, so you can tell tangent was used. It was out of section 9.4, and so this was not specific to any one of these two sections, which is nice. That's kind of how trig should generally be used and thought of. Number 3, oh, this is all based off SOHCAHTOA, by the way. Let me write that once and then see if you got it. SOHCAHTOA. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. Tangent is opposite over adjacent. Number 3, looks like I don't want to use sine this time. K and J are not known. I know this adjacent side, 10, hypotenuse, can be used there to find J. So let's start with cosine. I've been using green for cosine. Let me do that again. So cosine of 40 degrees is 10 over J. J will be 10 divided by the cosine of 40. Should be larger than 10, of course. Ugh. So 10 over cosine of 40. I'm getting 13.05. That's around 13.1. More than 10, yes. K, opposite and adjacent. Let's use tangent. Tangent of 40 degrees equals K over 10, although in this case we get to multiply both sides by 10, and K is 10 times tangent of 40. Should be less than 10. So 10 times the tangent of 40, I'm getting an 8.39, so around 8.4. And there are the first 3 problems there using some trig, and kind of the ways that trig is generally used. Numbers 4 through 6. Verify the segment lengths form a triangle. Is the triangle acute, right, or obtuse? This was out of section 9.1 using the Pythagorean theorem, and in this case, the converse of the Pythagorean theorem. In the Pythagorean theorem, a squared plus b squared equals c squared in any right triangle. And if in a triangle, a squared plus b squared equals c squared, then it's right. If a squared plus b squared is greater than c squared, it is acute, and if a squared plus b squared is less than c squared, it is obtuse. Those are the tests we're going to do. I'm going to begin with a test of whether 16 plus 30 is indeed greater than 34. I think we all agree that it is, and if I show you that 46 is this number, then we can get to that. So this is a triangle. It's a triangle. Is it a right triangle? Is it acute? Is it obtuse? This is where we do 16 squared plus 30 squared and compare it to 34 squared. Excuse me. This is an 8, 15, 17 Pythagorean triple. I already know what this thing's going to be. I just don't know. Hold on, 256 plus 900. This must be 1156. I know my Pythagorean triples. So 1156 and 1156. These are equal to each other. No, I didn't know 34 squared, but I know 34 is twice of 17, 30 is twice of 15, 16 is twice of 8. It's an 8, 15, 17 Pythagorean triple, one that exists in a right triangle with those integer values. So it's similar to it. Therefore, what kind of triangle is this? Right. This is a right triangle. Helps to know those. Number 5. Clearly not a Pythagorean triple. Doesn't mean it's not a right triangle. Let's compare 4, the square root of 67, and 9. Now, you do want to make sure when you do your triangle test, like, is it a triangle? Make sure that you have the 2 smaller sides on one side and 9, the longest side on the other. Is that so? I know root 67 is less than 9 because root 81 is 9. But I don't know what root 67 is. It's a little more than 8. So I know this will be more than it. Root 67, y'all, is 8.18. So let's just say 4 plus 8.1. 8.1. How's that compared to 9? Around 12.1. That is greater than 9. This thing checks out. It's a triangle. What kind of triangle? Let's do 4 squared plus root 67 squared to figure that out. And compare it to 9 squared. Is it greater than, less than, equal to? 16 plus 67. 9 squared is 81. 16 plus 67 is 83. How does 83 compare to 81? It's greater than it. If a squared plus b squared is greater than c squared, assuming c is the longest side of the thing you chose, you have an acute triangle. And that's what this is. Maybe barely acute, but acute indeed. That was number 5. Number 6. Root 5, 5, and 5.5. I forget what root 5 is. 2.2 something. So root 5, 5, and 5.5. A lot of 5s. Let's make sure. Root 5 is the smallest for sure. Plus 5. Is it greater than 5.5? Yeah. I'm going to say it's around 2.2, I believe. So let's say 2.2. and that's 7.2. 7.2 is greater than 5.5. This is a triangle. Let's figure out what kind it is. Probably the obtuse one. It would be nice if we have one of each type. Let's try root 5 squared plus 5 squared and compare it to, whoops, not equal to. We don't know that. Root 5 squared plus 5 squared and compare it to 5.5 squared, which I do not know what 5.5 is. 5 plus 25. Well, 5.5 squared is 30.25. Ooh, very close. Check this out. This side's 30. This side's 30.25. C squared is bigger than a squared plus b squared, even if just barely. That's enough to call this triangle obtuse, if not equal, but yet greater than. And that's number 6, or numbers 4 through 6. Numbers 7 through 9, we are going to solve the triangle ABC. This is something out of section 9.6, round decimal answers to the nearest tenth. As you've probably seen me do before, I'm not going to round early on values. I'm not going to use rounded values to calculate other values. I will always use exact, and I will refrain from trying to use those rounded values completely to find these other ones, which I think I can always do. So number 7, to find the length of AC, I can do 11 squared plus 5 squared is AC squared. Do a little sprinkle of 9.1 there. 121 plus 25. All right, AC is the square root of 146. No need to do simplifying radical procedure, which I don't think it can simplify. We're just going to round to the nearest tenth. 12.08 is around 12.1. And that is the approximate length of AC. So I want to avoid using AC, though, when it comes to finding angles. It is rounded. Let's say we want to find the measure of angle A. I'm going to use the opposite and adjacent. It means I'm going to use tangent. So if I want to take the tangent of angle A, I'll use opposite over adjacent, 5 over 11. So the measure of angle A will be the inverse tangent of 5 over 11. So my calculator will help me with that. Inverse tangent, don't hit tangent, but inverse tangent, be sure you're in degrees. I get 24.4 degrees. Fahrenheit, Celsius, no, just an angle measure, 24.4 degrees. Measure of angle C is going to be 90 minus that, which is about, trying to do it in my head, 65.6 degrees. And that's the last one. And that solves the triangle. That's every missing part that I'm looking for. I could have found C first by doing inverse tangent of 11 over 5. I should get that answer. Okay, number 8. Same setup when it comes to two known sides and no known angles, but this time the known sides are, one's a leg, one's a hypotenuse. Oh, let's copy paste this. My bad. All right. All right. Let's find this side length AB. It's one of the legs. AB squared plus 11 squared equals 18 squared is our initial setup. Not a Pythagorean triple. Let's keep moving forward. No, 203. 324 AB squared equals 203. Square root of 203. 14.2, sure. It's approximated. 14.2. So here is this guy. Making sure all that math lines up. I believe it does. Okay, let's find the measure of one of these other angles. I'm looking ahead. Let's find the measure of angle C. How about right here? I don't want to use the 14.2 though. It's rounded. Let's use the adjacent and hypotenuse. Let's use cosine. Cosine of angle C is adjacent over hypotenuse. So C, measure of angle C, equals the inverse cosine of the adjacent over hypotenuse, which is about 52.3 degrees. right here. And just like the last problem, I can find measure of angle B by doing 90 minus that other one. So measure of angle B is 90 minus 52.3. That's a decimal, which is about 37.3. I only hope I'm doing that part right. I'm telling you out loud what my work is that I'm doing, just in case I do screw it up. You can try it for yourself and say, Mr. Robinson, you screwed up. I think I'm okay. Number 9. This is a right triangle. It's a little rotated over. But the hypotenuse is 9.2. Don't make the mistake of thinking anything else is that hypotenuse. So number 9. I have hypotenuse and that long leg. Let's find that short leg of CB or BC. So BC squared equals 8 squared plus 9. Oh, excuse me. BC squared. BC squared plus 8 squared equals 9.2 squared. If you think I know what 9.2 squared is, you would be sorely mistaken. BC squared plus 64 equals, it's exact, something I can write exactly, 84.64. So BC squared is 20.64. What's the square root of 20? Let's see, square root. That's what I got to do. Take the square root of both sides, and I get around 4.5 units in length, and that is BC. Okay, let's find measure of angle B. This time I'm going to use inverse sine. The sine of B is 8 over 9.2. That's my opposite over hypotenuse. So sine of B. Interesting how none of these problems, how do you solve the triangle with one of the angle measures? See, this you have to... Sorry, this is me griping. I just came off recording the Chapter 9 video, and I said, there's certain kinds of problems that aren't touched. This time in the Chapter 9 test, there's not one that's touched that says solve a triangle where one of the angle measures was known. We never did that in any of these problems here. So refer to some of the Chapter 9 review if you want to see more problems of the sort. This is really why I'm hoping there's an Are You Ready thing. I really wish the bookmakers were aware that they didn't diversify all their kinds of problems, but I guess they're testing you on what they want to choose to test you on. Inverse sine of 8 over 9.2 is around 60.4 degrees. So 60.4 degrees right here. And then A is going to be 90 minus that 60.4 degrees. Measure of angle A is 90 minus 60.4 degrees, which should be about, what, 29.6 degrees? And that's solving this triangle. Okay, like I said, there are other kinds of problems where there are ones where you have only one side length and then one angle measure, and you can still solve the triangle using trig. I believe my Chapter 9 review had at least one of those problems. All right, number 10, find the geometric mean of 9 and 25. This comes out of section 9.3, where we had the similar right triangle stuff. So, number 10, geo mean of 9 and 25. Let me give you the precursor before this thing. It's the value in between that I can multiply 9 by something to get that, and that by something to get 25. So if I divide 9 divided by that something, and that something divided by 25, they should be in proportion. When I cross multiply, and this is the part that you might set up more often, is 9 times 25. Now 9 times 25 is something. It's actually 225, but if you didn't know what it was, taking the square root now is a good business, because 9 and 25 are perfect squares. This is 3 times 5. That's 15. 15 is the geometric mean of 9 and 25, as in 9 times some number is 15. It's a fraction. It's a not an integer. 9 times 5/3 is 15, excuse me, and 15 times 5/3 is 25. Makes it the geometric mean. That's number 10. Number 11, write cosine of 53 degrees in terms of sine. Well, cosine of one measure is the sine of the complement of that measure. So cosine of 53 degrees is sine of 90 minus 53 degrees. So that will be sine of 37 degrees. Those are both the same value. Try it in your calculator. Cosine 53, sine of 37. I have no idea what they are. I know they're a little more than 0.5. Don't know what they are exactly, though. Numbers 12, 13, and 14. Find the value of each variable. Write your answers in simplest form. These are different kinds of questions, though. Number 12 is a trig-based question. It's either 9-4 or 9-5. This actually is just like, oh, no, it's not. That is not trig. I take it back. This is 9-2. This is special right triangles. 14 is also a special right triangle, but 13 is a similar right triangle scenario out of 9-3. So those are all different things there. Let's copy and paste these. Let's get them ready to go. Sorry, this little 9.2 is going to come up in the copy paste job. I'll hide it. Get out of here. You don't belong. Whoa. There we go. All right. So number 12. This is a 1-to-1 to root 2 ratio relationship in a 45-45-90 triangle. 16 and R are 1-to-1, therefore R is 16. They are congruent to each other. Q, on the other hand, is root 2 times larger than either of these things. So it's 16 times square root of 2, which is 16 root 2. Done. Number 13. Not a special right triangle. It's just right triangles that are all similar to each other. So, boom. On number 13, we have 3 different variables to solve for with this information. Let's see which one is just easiest to solve for, which one I can kind of make shift here. I want to see what's represented here. Like 16 is the hypotenuse of the whole big triangle. 14 is both the hypotenuse of the big and the long leg of the medium. So let's find something else in the medium triangle I want to find, such as the, it's the hypotenuse of the medium and the long leg of the big. So here's the long leg of the medium, C. I think I can find that one first. I can do long leg of medium over long leg of big equals hypotenuse of medium over hypotenuse of big. This is, of course, 14 is the geometric mean of C and 16. When you cross multiply, you'll find out that 14 squared is 16 times C. I'll say C times 16 to bring up this whole thing. This squared equals this times this. That's the thing the book wants to tell you. That squared equals that times that. That's how I kind of set it up for you. So 14 squared is 196. And divide by 16, you get C equals, I have no idea. Let's bring that back to 14 squared. 14 times 14 over 16. This reduces to 7/8. 14 over 8 reduces to 7/4. 49 fourths. 49 fourths, which is also 12.25. There, look at that non-calculator biz. That was fun. Simplest form, there's simplest form. There's also a decimal version for C. Now, I can use that value. It's exact. And I can use it if I need to for other values such as D and E. And I might have to. You know, E can be found multiple ways. You do not have to use this proportionality stuff to find E. I could use Pythagorean theorem to find E. In fact, I might want to do that for this problem. E squared plus 12.25 squared equals 14 squared. This is this medium right triangle right here. I can use that. What's wrong with that? Nothing. It's probably not how they want you to solve it, but you can. 12.25 squared is 150. 150.0625. Probably not the way I want to do it, actually, suddenly. 14 squared is 196, sorry. Maybe I'll still find it another way, right? I just want to use this knowing that I could. Trying to think. Oh, D is also pretty straightforward with what I can do on D, by the way. I'll tell you that. E squared is 45.9375. So E, boy, that's not going to be a fun square root. It says simplest form. Maybe I have to... E is square root of this. So, okay, maybe not the best use of that stuff. That's one version of that answer, but I don't love it because it's not something I love. I don't know if there's a better version I can use yet, except D. What's D? D is just 16 minus this guy. So D, let's use a different color. D is 16 minus 12.25, which is 3.75. That's D's value. D equals. So there's that guy. Yeah, E's not going to look much better than what I have here. Let me show you another version of E now that I have the 3.75. E represents both the long leg of the small triangle and the short leg of the medium triangle. So I could say the long leg of the small is to the long leg of the medium, as the short leg of the small is to the short leg of the medium, like that. If I cross multiply, I get E squared equals, and you know what 12.25, you know what 12.25 times 3.75 is? I'll let you guess. It's 45. It's 45.9375. Where have I seen that before? It's here. So you know what I want to do instead is this. It says simplest form. Remember this 49 fourths that I have? I want to use that. I want to write these all as these kinds of answers. 49 fourths, geez. C is 49 fourths. D is 16 minus 49 fourths. That's 64 fourths minus 49 fourths, which is 15 fourths. D is 15 fourths. And let's use those to find E. E squared was that C times D. Whoops. Times D, 15 fourths. And let's work off of this instead. Instead of multiplying straight out, let's work off square roots now. Square roots of these. E is 7 halves times root 15 halves, which is 7 root 15 over 4. That's the exact answer for E that I'm looking for. The square root of this is that value. That's probably the best way of going about it, using fractions, not decimals. And I'm sure that's one where an answer key would say something like that. So I still used everything. I know it took a little bit longer, and Pythagorean theorem could have still worked. I just had to use the fraction version of it. All right, number 14 is actually going to go relatively fast in comparison to that last problem, which had quite a bit of whirligigs. So number 14 is this. This is a 30, 60, 90 triangle, which has a 1 to 2 to root 3 ratio relationship among the short leg, hypotenuse, and long leg, respectively. Now, this is an interesting kind of question. It's not interesting, but we didn't get a kind of question like this in the Chapter 9 review part of the textbook, so I'm glad we get it here. I have the long leg of 8. To get to F, I need to divide 8 by the square root of 3, because it's root 3 times larger than the short leg. That's 8 root 3 over 3 when rationalized. That's the way that we say that. So F is 8 root 3 over 3. H is twice the amount of the short leg. So H is just 8 root 3 over 3 times 2, which is 16 root 3 over 3. Not much else to it. That's just going to be the answer. And that is it. Much faster than the previous problem. Okay, let's keep going down. Let's look at number 15. I'm going to do this in a way that I prefer best. Cosine of theta is 5/7. Find sine and tangent of theta. I'm going to basically draw a right triangle where there's an angle theta, and the adjacent leg is 5, the hypotenuse is 7, so cosine of theta is that. Let's find this unknown side right here, x, and figure out what that is. So x squared plus 5 squared is 7 squared, not a Pythagorean triple. So x is going to be 2 root 6 when all is said and done and simplified. So x is 2 root 6. Now I can find the sine and tangent of theta because that's the opposite. For sine of theta, I need opposite over hypotenuse. That's 2 root 6 over 7. That's the answer. And tangent of theta is 2 root 6 over 5, opposite over adjacent, and that's the answer. So those are them based on that information provided. That's number 15. Okay, number 16. You are given the measures of both acute angles of a right triangle. Can you determine the side lengths? Explain. If that's all you're given, no. So no, because all triangles of that angle measure set are similar. So no. Unless a side length is given, you are simply given angle measures of what would be similar triangles and can grow or shrink to any, enlarge or reduce to any side length amounts which remain in proportion to one another. So You know that whole 1 to 1 to root 2, like, okay, so say this, for example, right? I have a 45, 45, 90 triangle, but let's say that that's all you know. See, I write 1, 1, and root 2. That doesn't mean those are the side lengths. This is just how they compare to each other. For all I know, these could be 11 and 11 and 11 root 2. I don't know. But can I determine the side lengths? Not if that's all I'm given. I need to know a side length. Unless the side length is given, no, I cannot. All right. Number 17. 2 more questions before we do the cumulative assessment part. Number 17, you are at a parade looking, here's the diagram, looking up at a large balloon. I feel like I need to copy paste this because they have information. Oh, they have information. All right, you're at a parade looking up at a large balloon in a generic city. Floating directly above the street, you are 60 feet, right here, you are 60 feet from a point on the street directly beneath the balloon. So here's me. Here's the point on the street directly beneath the balloon. To see the top of the balloon, you look up at an angle of 53 degrees. That's me looking at the top. To see the bottom of the balloon, you look at an angle 29 degrees. Estimate the height of the balloon. So what we want to do is establish that there are basically 2 right triangles here. And we will subtract those values from each other when we establish what they are. I got a big right triangle here. And then I got a smaller right triangle, here. They both have their respective angle measures, and this 60 is shared for both of them. So in green, if I want to find this entire X here, if you will, I can use the 53-degree angle, the 60-degree angle, which is adjacent, and X is opposite. I want to use tangent. Tangent of 53 degrees is X over 60. So X is 60 times the tangent of 53. I'm not going to round this just yet. I'm just going to go ahead and leave it like that. So X is this guy. If I want to find this guy Y, it's the same kind of setup using the 60 and tangent because it's opposite and adjacent, but with the 29. So guys, Y is going to be 60 times the tangent of 29 degrees. Believe that when it comes to opposite over adjacent being the same thing, like that. So the height H, yeah, this is why I often don't use red. It's a little bouncy in look. H is going to be X minus Y, which is going to be 60 times the tangent of 53 minus 60 times the tangent of 29. So that's what I'm going to use the calculator here. So 60 times the tangent of 53 minus 60 times the tangent of 29 gives me about 46.36. What do they want us to round to? I don't know. I'm just going to say 46.4 feet. It's about the height of the balloon. So I took whatever the height of this was to the top of the balloon, height of this to the bottom of the balloon, and I subtracted them to get the final. That's why I worked it that way. And the last question on this part, number 18, you want to copy and paste this. You want to take a picture of a statue on Easter Island. I was going to say it looks like the Easter Island statues. Ugh, those are creepy. Called a moai. I'll say moai. The moai is about 13 feet tall, so that's not labeled. Let's go ahead and label that for ourselves. Here's the moai, about 13 feet, and let's use that approximation for the problem. Your camera on a tripod is 5 feet tall, so this is 5 feet. And the vertical viewing angle of your camera is set at 90 degrees, so that is the right angle here. How far from the moai should you stand so the entire height of the moai is perfectly framed in the photo? Interesting question. How far should you be from there? So there's a right triangle within here as well, where this is 5. That's 5 right there. And then I can use that. Your camera's on a tripod that's 5 feet tall. The vertical viewing angle of your camera is set at 90 degrees. How far from the moai should you stand? Entire height. I'm trying to see where 5 is used. I guess I can build a triangle inside here, rather. So this 5 can also be right there. Now, how does that assist me with what I need? That makes this guy 8. 13 and 90. Do I know any other angles here? 5. That's not bisected. Oh, this is the altitude thing. This isn't trig. This isn't trig. Interesting question then. Okay. So this is an altitude built within... This is cool. This is an altitude built within a triangle here. This 13 is there. What I could find first... What are they asking? How far from the moai should you stand? Eventually, I need to find out this length here. This x. I'll get to there. I need to first... Well, not first. 13 minus 5 is 8. I need to first figure out that's 8. So I need to find out this x, which is the same as this x, if you will. Right there, this altitude. So imagine I have this, okay? I have a right triangle. And inside that, I have an altitude. And I know that this is 5, and this is 8, and this unknown x. This is one of those right triangle similarity things. I was like, where are my angles besides 90? Okay, cool. So long leg of the medium over long leg of the small equals short leg of the medium over short leg of the small. X is the geometric mean of 8 and 5. When you cross multiply, you get x squared equals 8 times 5. So x squared is 40. X is the square root of 40. That'll be 2 root 10. Now we will round that. Root 40. I know it's somewhere around 6.5 something. Square root 40. 6.32. I'll say 6.3 feet. That's how far I should be, so it's perfectly framed in the photo. Interesting question. I like that it kind of made me think a little bit there. All right, guys, that is the end of the, not whole video, but the end of the chapter 9 test. If you want to stop there, you can. Let's jump into the cumulative assessment in case you want to hear some more things. Again, this is a brand new PDF that I use. If you are trying to download, go to the description section down below and you can find it here. Let's go ahead and keep going. Oh, by the way, that's okay. That would have been out of section 9.3. I stopped writing sections probably a little bit ago. I'm sorry. Number 1, the size of a laptop screen is measured by the length of its diagonal. Very true. So as in like, how long is that is what they're saying. You want to purchase a laptop with the largest screen possible. Which laptop should you buy? Let's figure out which one has the biggest version of 1 squared plus the other squared. Even if I didn't find out this length for all of them, it's whatever the square root of those numbers are in comparison to each other. Now, I can tell you that this one, just by knowledge, is going to be 15 inches. This is a 3, 4, 5 Pythagorean triple. But I think what I want to do here is not find the actual lengths because I want to save myself time on square root stuff. I'm just going to go ahead and do 1 squared plus the other squared. So laptop A is 12 squared plus 9 squared, and that ends up being 225. Let's compare it to the others. B is 20 squared plus 11.25 squared. Automatically, know that's more than 225 because 20 squared is 400. So we'll use a calculator for that. So 400 plus 11.25 squared. Again, spare me your square roots. 526.5625. I don't know how exact I need to get, so I'm going to write them all. So definitely not A. A is out. Sorry, small laptop. C, 12 squared plus 6.75 squared. I think you can notice that this is going to be less than B. Can I just say it's B? B automatically has the biggest numbers already. I didn't know if this was a Pythagorean theorem question or not, but yeah, this is already bigger. You know what else? Oh, never mind. That's not true. Never mind. But yeah, the answer is going to be B. Let's figure out what 12 squared plus 6.75 squared. I guess while I'm calculating these, I might as well get their square roots. I'm not actually going to. Let's rank them. I mean, of course, it's less than 12 squared plus 9 squared. Clearly, C is out. Yeah, B is going to be the answer. I didn't look hard enough at the other values. I thought they were going to test us. 8 squared plus 6 squared, that'll be 100. I know that one. So that's the smallest one. Okay, so the answer is B on number 1. I don't know if they meant for you to just look at them and say, here you go. That's kind of interesting. Okay, that's number 1. Number 2. I don't even know. Honestly, I don't even know what chapter that's from. I don't even know if that's a Pythagorean theorem question. A similarity. It's not similarity, so it must be Pythagorean theorem. I don't even know. All right, number 2. In triangle PQR and triangle SQT, S is between P and Q, T is between R and Q. Whew. And that over that is that over that. What must be true about ST and PR? Select all that apply. Let's draw something. Let's draw a triangle and see what the heck they're talking about. Here's PQR. Oh, SQT. That's a Q. So SQT. S is between P and Q. They didn't say in the middle, but they said between. T is between R and Q. And there's that. Okay. And QS, this guy, QS over SPO is QT over TR. QS over SP equals QT over TR. This is in chapter 8. This is, I think, section 8.6. 8.6, I believe. This is the converse of the triangle proportionality theorem. If this is true, then a couple things are true. I know that ST is parallel to PR. That's a for sure. So let's see. ST parallel to TR is on the docket right there. It's not necessarily equal. Is it half of PR? Not necessarily. Only if it is a midpoint. This is the only thing that's a for sure true. So look, ST is not perpendicular to PR. You can see from the drawing. ST is not equal to PR. I'm sure you can see from the drawing. Because it's in between, it's not on P, it's not on R, and it would only be half if this was a midpoint, meaning these were congruent like that. So that's not a guarantee. It could be, but that's not the case for this one. That's the only one in question there. That's from, I think, section 8.6, chapter 8. Number 3. This is chapter 8 as well. In the diagram, you have two similar triangles. They are 3, 4, 5 Pythagorean triples. Triangle JKL is similar to triangle, oh, actually it's more chapter 9. Look at these trig functions. Triangle QRS, choose the symbol that makes each statement true. You know what would be nice to do is redraw these so that they face the same direction of each other. So if I say JKL, like so, and I have 6, 8, 10, and then redraw QRS in the same direction, because you know what? You could confuse what goes where. Q goes with J. It goes right there. So this is more of a reflection. R is the right angle and S is here. Q is 3. Q is 3. These aren't even supposed to be blue. QRS. QR is 3. RS is 4. 3, 4, 5. Boom, like that. Okay. What do they want? Choose the symbol that makes each statement true. They use sine, cosine, and tangent of all three of them. Let's write out what we're looking for. Sine of J is 8 over 10, which is 4/5, which is going to be the same, by the way, as the sine of Q. Hold on, let's do this. Sine of J is going to be the same as the sine of Q, which are both 4/5. The cosine of J is equal to the cosine of Q. Oh, hold on. I'm going to do even more than this. The sine of J equals the sine of Q equals the cosine of L equals the cosine of S. Those are all 4/5. The cosine of, let's do this. The sine of L is definitely chapter 9. Sine of L equals sine of S, which is the same as the cosine of J and the cosine of Q. J and cosine of Q, that is not a Q, which are all 3/5. It's good to write these out beforehand. Tangent's going to be its own animal. Tangent of J is going to be the same as tangent of Q, which will be 4/3, opposite over adjacent. And the tangent of L is going to equal the tangent of S, which is 3/4. Now, in terms of order for these ones themselves, 3/4 is 0.75, 4/3 is 1.3 repeating, 3/5 is 0.6, and 4/5 is 0.8, in case you weren't sure how those fractions worked out. So the biggest is the tangent of J and Q, and then it's these ones, and then those ones, and those ones. So let's check them all out. Let me copy paste these, and then I'll write down what they are. It really helped to get those in first. I don't even need the diagram anymore, although that took a while. But now that I have them in place, I think it's really going to help out. Okay. Here we go. Sine of j and sine of q. Those are equal, right? They're equal. Cosine of s, cosine of j, cosine of s, cosine of j. 0.8 is more than 0.6. Cosine of s is more than cosine of j. Tangent of L, 0.75, is less than tangent of Q, which is 1.3 repeating. Sine of L, cosine of J. Sine of L, cosine of J are equal. Cosine of J, sine of S are equal. Tangent of S, 0.75. Cosine of Q, 0.6. Tangent of S bigger. Probably would have been faster for me to say, well, I don't know. This is pretty fast now. Cosine of L, tangent of Q, tangent of Q is going to win. So tangent of Q wins. Tangent of J also is going to beat anything except for tangent of Q. Those are equal to each other. And sine of Q and cosine of L are equal. There we go. Those are them. Nicely done. Nicely done. All right, number 4. Maybe that's the only one out of chapter 9. I still haven't done a video for chapter 5, or videos for chapter 5, but that's number 4. Out of 60 students, 46 like fiction novels, 30 like nonfiction novels, and 22 like both. What is the probability a randomly selected student likes fiction or nonfiction novels? Maybe I'll Venn diagram it as a teaching moment, because I haven't really talked about these ones quite often for a while. Actually, I haven't talked about them yet in any video here. So to Venn diagram this out, the idea behind this is you have fiction novels, likers, nonfiction novel likers, both, and nobody. The fiction novels, 46, that's for this and the both. And then the 30 is for that and both, and 22 is literally for both. You got to do 46 minus 22 to figure out how many people are here, which is 24. So 24, now get rid of the 46. 24 are how many exclusively like fiction. And then the 30 minus 22 is 8. 8 exclusively like nonfiction. See, 22 that like both. 8 plus 22 is the 30 who like nonfiction. 24 plus 22 is the 46 who like fiction. 24 plus 22 plus 8 is how many like fiction or nonfiction in total. Because there's overlap of the 22 that are there. So 24 plus... There are other ways I can write this, by the way. I'm just coming up with one version of it. 24 plus 22 plus 8 is 54, which also means 6 like none of them. Okay, so to find out how many probability fiction or nonfiction will be 54 out of the 60 that are there total, that's 0.9, which is 90%. So 0.9 is that, or 9/10. Let me write the 9/10 somewhere. 54 over 60 is 9/10. Okay, that's a visual version of that. If you want a more just formulaic version of that, something that we would do, probability of fiction is 46 out of 60. I'm going to leave them out of 60 for now. No reduction, no decimal. Probability of nonfiction is 30 out of 60. Probability of fiction and nonfiction, we kind of use this N for that, the lowercase n thing, intersection. Fiction and nonfiction is 22 out of 60. So the probability of fiction or nonfiction, fun, probability of fiction or nonfiction is 46 out of 60 plus 30 out of 60 minus 22 out of 60. You take how many like fiction, how many like nonfiction, but there is overlap of 22 students who were counted twice, so we take out that result. So the probability of fiction or nonfiction is going to be 76 minus 22, which is 54, and that's where we get to, once again, the 9/10, which is 0.9, which is 90%. So we saw that same thing there. There's the formulaic version of that, probably the better off one, but I wanted to give you a Venn diagram appearance of it. How many didn't like any of them? It's 10%, 6 out of 60. All right, that's out of chapter 5. Number 5. Oh, also out of chapter 9, more cumulative assessment. Right, create as many true equations as possible. Blank equals blank here. So for one, this is a 30, 60, 90 triangle setup. I don't know if that's going to matter quite yet. But the sine of x is sine of 60. That's root 3 over 2. So sine of x equals root 3 over 2. That's the same as cosine of z. Sorry, it's just opposite or hypotenuse, adjacent or hypotenuse, stuff like that. Sine of x is cosine of z, which is also the same as yz over xz. The sine of z should be equal to the cosine of x, which are 3 over 6. That's 1/2. That is xy over xz. Those are all true. It says create as many equations. So here's one of them. Here's another. Here's a third. Here's one of them. Here's another. Here's a third, right? I'm writing them like this. I hope that's okay. Otherwise, I'd be writing here all day. I don't want to have made 6 equations instead of that. And then tangent. Tangent of z. Let's do tangent of x first. Tangent of x is yz over xy. Yz over xy. And then tangent of z is xy over yz. Yeah, so I kind of cheapened out on this first part here. Sorry. You know what? I won't cheapen out, but I just got to do some copying and pasting. Give me 1 second. Let's go and move these down. Sorry if you already started writing, but I'm going to do this. Give me a second. Okay, let's erase these guys here. Oh, there's some overlap there. So let's erase these guys here for one set. Let's erase these guys here for another set. Boom. It's probably faster to have written these. And let's erase these guys here for a third set as we bring these into the fold. Here. There we go. I think those are all the equations I could write. There's number 5. Number 6. Prove. We have to do a proof. Prove the quadrilateral DEFG is a kite. That's out of chapter 7, I believe, and that was 7.5. I think it was 7.5. Given, well, let's copy and paste that. Even the part that says prove that it is. Get the diagram, get it all in. That's right. That's right. Get it all. There we go. Okay. So we'll go statements and reasons on this guy here. Let's do statements and reasons. I don't know how long this will be, though. To prove this thing's a kite, what we want to do is basically show that the kite's definition is that it has 2 sets of consecutive sides that are congruent. So I think I just want to find a way. I'll use like CP, kind of stuff. But I want to find a way to say that this is congruent to this and this is congruent to that. I basically want to show that 2 different sets of triangles are congruent to each other. I want to prove that this triangle is congruent to this one and this triangle is congruent to this one. And I think I can use like the same step in each one. So like just like on 1, they say that HE is congruent to HG. Let's mark up where that is. Oh, it's already marked. HE congruent to HG, which exists in both triangles. HE exists in this triangle and that triangle. HG exists in this triangle, that triangle. And EG perpendicular to DF also technically exists in both triangles because all these are now right angles, right? In fact, we might prove this using HL. No, probably side angle side. So that's given. Let's go to the reflexive property to show some other things that are congruent to each other. This thing's congruent to itself. This thing's congruent to itself. That's kind of what I'm bringing up there. So HF congruent to itself by the reflexive property. And then DH congruent to itself by the reflexive property. So like I said, I'm doing the same reason for kind of 2 different triangles here. I'll use the right angle portion. You know, it said they're perpendicular. Now we want to state these are all right angles. 1, 2, 3, and 4 of them. So let's use a different color though, because I want to write out what I'm using. State that they're right angles so that they can say that they're all congruent to each other, right? So on 3, I can say angle, the first one they gave us there was the EHF. Angle EHF, angle, there are a few of them. GHF is right there. angle GHD, boom, and then angle EHD. GHD and angle EHD are right angles. This is the definition of perpendicular lines. The fact that they made the statement means that we can use that. Hold on, I want to make sure I'm still on my video capture. I am. Okay, let me scroll down because I don't want to lose that part. So definition of perpendicular lines. What I also want to do is make those green. So green and green. It's okay if the 3 is green? Yeah, if I make the 2 blue. All right. Perfect. Okay. So they are all right angles and they're all congruent to each other. But more specifically, in this triangle and this triangle, to show those are congruent, I want to say this is congruent to that, and I want to say this is congruent to that. Sure, they're all congruent to each other, but I want to show in the specific triangles I'm going to make congruent be that case. So I want to say EHF and GHF are congruent. Angle EHF is congruent to angle GHF, as all right angles are congruent. And then angle, what is it, GHD and EHG. GHD and EHD are congruent. That is, not definition of right angles. Right angle theorem? Is that what we call it? I say all right angles are congruent. I think I've been calling it the right angle theorem. Okay, now 2 sets of triangles are congruent by side angle side, right? I got side angle side with side angle side here, and then side angle side with side angle side right there. So we can call it, I think these letters correspond, so I think I'm going to stick with that. So triangle EHF is congruent to triangle GHF, and then triangle GHD is congruent to triangle EHD. That is they are the side angle side congruence theorem reasonings there. And because of that, we can now kind of use CPCTC, not kind of, we can, that now this segment is congruent to this segment, and this segment, a lot of tick marks, is congruent to that segment there. So EF is congruent, oh, right here. FE is congruent to FG, and DE is congruent to DG. FE, let me write them first, what I need to see. FE is congruent to FG, and DE is congruent to DG. Okay, I wrote this down here. That is by CPCTC. Corresponding parts of congruent triangles are congruent. That is the proof. We are done. I didn't even realize, I didn't even look at this proof part to say what I needed to prove to say that it's a kite. They're saying prove it's a kite, and kite is the proof. I didn't even see that, but yes, kite by definition has 2 sets of consecutive sides that are congruent to each other. I probably should have looked at the proving step, and we are there. So I don't even have to say it is a kite. I am done. All right, 3 more questions. We have number 7. The area of the triangle is 42 square inches. I don't know what section this is out of. Find the value of x. Yeah, I don't know which thing. I don't remember. But the area of a triangle is 1/2 base times height. And let's look at that diagram. Our base can be, base can be x plus 8, and height can be x. So the area of the triangle is 1/2, I guess chapter 2, this is quadratic stuff, x plus 8 times x. Oh, and the area of the triangle, sorry, is 42. So, oh, totally, yeah, this is like chapter 2 stuff. Or maybe chapter 4. I don't know what kind of solving this thing's going to be. Before I do any distribution of any sort, guys, I'm going to multiply everything by 2 and make this 84. 84 is, and I'm going to call this x times x plus 8, even easier. But times 2, boom, times 2, wipes out that one, and we're there. Now I have x squared plus 8x equals 84. I'm trying to see if this can factor first. Maybe? 16. Yes, it can. Let's figure out what it is, though. 8x minus 84 equals 0. All right, I need 2 numbers that multiply to 84. One's a plus, one's a minus here. 2 numbers multiply. Not 7 and 12, though. I got to figure out 14 and 6. X plus 14 times x minus 6. There we go. So x is negative 14 and x equals 6. Now, distance can't be negative, so negative 14 is out. That is extraneous. X equals 6 would be the only answer that should work out. To double check it, 6 plus 8 is 14. There's 6. Half of 14 times 6 is half of 84, which is 42. square inches. And that is x. Okay, that's number 7. It's out of chapter 2. Number 8. Classify, this looks like chapter 4. Classify the solutions of each equation as real numbers, imaginary numbers, or pure imaginary numbers. Justify your answer. I don't want to. I don't want to justify. X plus square root of negative 16 equals 0. Do I have to solve them? I guess it's worth solving. Square root of negative 16 is also 4. Whoops. Is also 4i. So x is negative 4i. That is pure imaginary. Pure imagination. It's pure imaginary because it only, I'm justifying words. It only has an imaginary term. It doesn't have a real term there. And that is part A. Part B. 11 minus 2i minus negative 3i plus 6 equals 8 plus x. Yeah, I guess we got to simplify these, figure out where they go. First of all, let's work on distribute. Let's simplify this side. Distribute the negative. That becomes plus 3i minus 6. And let's see what pans out. 11 minus 6 is 5. Negative 2i plus 3i is 1i. And here we're going to get, when we subtract 8, we get negative 3 plus I. So x equals negative 3 plus I is an imaginary number because it has both an imaginary and real term in them. So it's all about solving this, I think, in the end. We still got to do that. Part C, definitely chapter 4, though. 3x squared minus 14 equals negative 20. If I add 14 over, I get 3x squared is negative 6. Divide by 3, I get x squared is negative 2. Take the square root of both sides, I get x equals plus or minus I root 2. These are both strictly pure imaginary. Those are imaginary terms only with no real. It's not real. No real terms yet. Part D. X squared plus 2x equals negative 3. I can already tell that this is, it's not rational. It looks like it could be, but it's not. X squared plus 2x plus 1, I'm going to solve by completing the square, equals negative 3 plus 1. So that's x plus 1 quantity squared equals negative 2. Take the square root of both sides. X plus 1 equals plus or minus I root 2. But we get to subtract 1 over. Negative 1 plus or minus I root 2. That is imaginary. Solution set contains a real and an imaginary. Okay. Part E. X squared equals 16. Take the square root of both sides. X equals plus or minus 4. Don't forget that this is not like a Pythagorean theorem thing. 4 isn't the only answer. Plus or minus is the other one. Either way, these are both, I was going to say pure real, but these are real numbers only, not an imaginary. And then part F, x squared minus 5x minus 8 equals 0. Not factorable, but let's go ahead. I don't want to complete the square either. Let's go to the discriminant first and do b squared minus 4ac, which is 25, plus 32, which is 57. Now, I'm not going to continue solving. I know as long as this thing is 0 or greater, it will have real solutions, non-imaginary. So with the discriminant being real, that means, or the discriminant being positive, that means this will have real solutions as well. Now, my justifying for that answer is positive discriminant equals, a positive discriminant equals real solutions. Maybe irrational, but real. And that's number 8. And the last question, number 9, has 3 parts to them. The Red Pyramid in Egypt. Let's go here. I probably have to copy paste this thing. The Red Pyramid in Egypt has a square base. Okay. I wonder how that's going to be used, because it shows triangles here. Oh, I see some congruent marks on here now that I enlarged it. I didn't see that to begin with, actually. The Red Pyramid of Egypt has a square base. These are congruent marks right here, and that's a right angle. It's kind of just the way that it... Now I know why they said square. Actually, no, I don't. But that's a right angle. Remember, this is angled differently, so I might have to like redraw this so it looks right. But here, altitude and congruent and stuff like that. Anyway, that's what we're looking at here. A, B, C, D. Okay. I'm still reading this sentence over and over. The red pyramid in Egypt has a square base. Each side of the base measures 722 feet. So whole thing is 722. I don't know if that's going to matter, but if I divide it by 2, I get 361. Is that right? Yeah. 361, 361. The height of the pyramid is 343. Part A, use the side length of the base, the height of the pyramid, and the Pythagorean theorem to find the slant height AB of the pyramid. So, AB. Oh, the slant height. Wait a second. Oh, the height of the pyramid is 343. Oh. I take this back. This part here is not 343. I need to do, this is why they talked about square pyramid. So I'm going to redraw this. I don't even know what section this goes in because this is a 3D model. Interesting. So guys, let me introduce you to the 3D world of, or to the world of 3D. So here I'm going to make shift. I don't know which thing this would show up in chapter-wise, so I couldn't tell you. Let me introduce you to the world of 3D surfaces. Because the height is inside of here, right? If you can imagine this is a square pyramid like this, you know, like that. And this inner height, this guy is 343. Now that's important because, you know, each side length here is, let me not do that one. Each side length here is, let's do the right angle that way, 722 as a whole, which means this part is 361, and that's 343 of this guy right here, right? That's 343. Now they want to find the slant height here. This is where this visual comes into play for us that you see right here. This AB, that's this right here. This is AB. So using Pythagorean theorem, we can use the 361, which I believe is 19 squared, but that doesn't matter for this. So 343 squared plus 361 squared equals AB squared. Wow. Yeah, I don't know which one would introduce you to the 3D world to understand height versus slant height without them making the drawing for us, which they didn't do. I'm going to do a lot of calculator work here. 343 squared plus 361 squared. I'm getting, big number. AB, let's hope this is an integer, you know, Pythagorean triple kind of thing. 247970. It's maybe looking less likely. Seeing that it ends in 0. Let's see. Nope. 479.96. So AB is about 497. I said 479. AB is about 498 feet. All right, there's AB's length. That is part A. Part B. Find AC. Well, now that I have this, and remember, this is a rounded value, I can now use that here. This is my 498-ish value. So I will use the exact one that I have, but now I can say 498 squared plus 361 squared equals AC squared. So I'm going to square what I have in my calculator. I have this value here. I will square this one plus 361 squared. And I'm going to take the square root of this guy. And yeah, it's good that I do not use that rounded value. Now I'm going to get 615.05. So I'm going to say around 615 feet. So I'm getting this guy for the length of AC. Now part C says, name 3 possible ways of finding measure of angle 1, then find measure of angle 1. So 615 is this, 615 feet. Measure of angle 1 is right here. The measure of the angle, using these different values. Now, everything here, this is rounded, and that's rounded, 498 and 615. So let me redraw that. I have basically a right triangle where I have 361, 498, and 615. But of course, these are rounded, and here's the 1. So I could find measure of angle 1 by doing a few things here. I can either do the inverse sine, this is chapter 9 now suddenly, I guess it all was, of 361 over 615, again, that one's rounded. Measure of angle 1 as inverse sine of inverse cosine of 498 over 615, and inverse tangent of 361 over 498. Any of these three should get you the same answer. And I'm going to use the 361 over 615 because 361 is exact and I have the 615 in here already. So inverse sine of 361 over the previous answer there, I'm getting about 35.94 degrees. So 35.9 degrees on that guy. I feel pretty confident on that. I'm just going to say that it's doing all those. So those are the ratios that I have there. And guys, that ought to do it for this one. This is Mr. Robinson. Thank you so much for watching. I didn't know if this was going to be long or short. It's a little on the longer end compared to what I hoped or expected, but we got through it. Yeah, so with that said, let's skedaddle. This was the end of the Chapter 9 test stuff and cumulative assessment. Check out the description section down below if you want to find any of the timestamps and playlists and anything of the sort. Thank you so much for watching. Take care. I will see you in the next one.